This video will explain parts A, B, and C for the example that we had just looked at. First of all, the vector diagram needs to be created. So we're going to draw one vector, the first part of the airplane's flight, at south 40 degrees east, and a vector that represents a 200 kilometer displacement for that airplane. And then the second part of the flight is a 450 kilometer trip at north 20 degrees east. And as mentioned in the explanation, we could have taken this vector and drawn it right here, so off of the head of the first vector, and then use the triangle method or the head to tail method of finding the resultant. But we're going to illustrate the parallelogram method here. So first of all, I'm going to create two equivalent vectors and then complete the parallelogram. So now the parallelogram has been completed. The resultant will be the vector that extends from the two tails to the opposite vertex. And here it is. So there's the resultant of the two vectors drawn. Now, to determine the magnitude of this resultant, we need to add a little bit more information onto our diagram. First of all, we'll add on the magnitude of those equivalent vectors that were drawn to create the parallelogram. The magnitude of this vector is 200 kilometers, and the magnitude of the other vector will be 450 kilometers. We've created two triangles here, and that's what we're going to be relying on to find the magnitude of this resultant. If we focus in on this triangle up top, we have two sides. We're interested in that third side, but we need an angle. To determine an angle in this triangle, we first look at the two angles that we use to draw the vectors. The angle in here that was just drawn there, so between the two vectors, is 120 degrees. That was determined by taking 180 and subtracting off 20 and 40 to leave us with 120 degrees. Now, a property of parallelograms is that the adjacent angles in a parallelogram are supplementary. They add to 180. So if you know that this is 120, then that means this angle up here must be 60. Just like this angle down here must be 60. And this opposite angle, the one opposite the 120, must also be 120. So now that we know that we have two sides in the contained angle, we can find the resultant since it is opposite our 60-degree angle, and we're going to use the cosine law to determine that. And there we have it. Using the cosine law, we want to set up the magnitude of the resultant squared, which is opposite the 60-degree angle, and we get 390.5. So this is the resulting displacement of these two parts of this airplane's flight. So 390.5 kilometers from where it initially started. The next part of the question asks, what is the angle between the two vectors, the two initial vectors from our diagram? Well, that was something we already determined from part A. We needed to determine the angle between those two vectors, which was 120 degrees, so that we could figure out the contained angle in this triangle so that we could determine the magnitude of the resultant. So the angle between the two vectors is 120 degrees. The last part of the question, part C, requires us to figure out the quadrant bearing of our resultant. To do that, we're going to again focus in on this triangle up top. We do know the resultant, or the magnitude of the resultant right now. So we have this side marked R, the magnitude of that vector. We do know its opposite angle, 60 degrees. We're going to find this angle that I've marked theta. Okay. The reason we want to find that is we could then add it on to the 20-degree angle, which was the angle of vector 2, that second part of the flight. If we can add theta onto 20 degrees, we will have this entire angle, which will help us find the quadrant bearing of this resultant. So the sine law can be used in this case. We want to determine theta. We know the side opposite it, 200 kilometers. And we have an angle side pair since we know the magnitude of our resultant and the angle across from it. So setting up the sine law and solving for theta, we end up with 26.3 degrees. Notice that we used a lot more accuracy in our resultant than what we ended up with here. The reason that we did this is so that we end up with more accuracy in our final answer for theta. So theta in our diagram must be 26.3 degrees. So I'll mark that in. This is 26.3 degrees. Since we know that this is 20, we add 20 and 26.3 degrees to get 46.3. So the resultant is north 46.3 degrees east, so toward the east direction.